In this section, we will explore advanced arithmetic operations in assembly language. We'll cover how to use shift and rotate instructions, perform multiplication and division, while handling potential overflows, and see how to expand basic addition and subtraction using carry and borrow flags for multi-byte operations. Finally, we'll learn how to manipulate decimal values. Let's begin with how and why to use shift and rotate operations. Assembly language provides bit-level operations that can manipulate data very quickly and efficiently. Two of the most common are shift and rotate. A shift operation moves the bits in a register either to the left or to the right. When bits are shifted, zeros or sometimes a sign bit are inserted on one side, and the bits that are pushed off the other side are discarded. There are a few types of shift instructions. Let's look at a table describing them. The SHL or SAL instruction stands for shift left logical. Its effect is to multiply the number by 2 for each position shifted. The SHR instruction is shift right logical, which has the effect of dividing an unsigned number by 2. Finally, the SAR instruction, which is shift arithmetic right, divides a signed number by 2, preserving the sign bit. So, why would you use these shift operations? They're incredibly fast for multiplying or dividing integers by powers of 2. They are also useful for manipulating individual bits, for example, to extract flags from a status register. Now, let's talk about the rotate operation. A rotate is similar to a shift, but instead of discarding the bit that moves out, it wraps around and comes back on the other end so no bits are lost. The main rotate instructions are ROL for rotate left, ROR for rotate right, RCL for rotate left through carry, and RCR for rotate right through carry. The last two include the carry flag in the rotation. Let's look at some example code. We define a byte of data named num with the binary value 11001010. In our code, we first load this byte into the AL register. If we apply SHLAL, 1, we shift the bits one position to the left, effectively multiplying by 2. The new value in AL becomes 1001010. If we instead apply SHRAL, 1, we shift one position to the right, dividing by 2, and the value becomes 011001001. Now, if we use ROL, AL, 1, we rotate the bits to the left. The most significant bit, which was a 1, wraps around to become the new least significant bit, resulting in the value 100101001. The ROR instruction does the opposite. In short, use SHL and SHR for fast arithmetic, and use ROL and ROR when you want to preserve all the bits and just reorder them. Next, let's discuss multiplication and overflow. The MUL instruction is used for multiplying unsigned integers. The instruction takes one operand, which is a register or a memory location. This operand is multiplied by the value in the ALAX or EAX register, depending on the operand's size. The result is stored in a wider register pair to accommodate a potentially larger value. Let's review the register pairs. If you multiply an 8-bit operand with AL, the 16-bit result is stored in AX. If you multiply a 16-bit operand with AX, the 32-bit result is stored in the DX:AX pair. And for a 32-bit multiplication with EAX, the 64-bit result is stored in EDX:EAX. For example, if we move 10 into AL and 20 into BL, the instruction MULBL will multiply them and store the result 200 in the AX register. For signed integers, we use the IMUL instruction. It handles negative numbers correctly and is more flexible as it can take 1, 2, or 3 operands. For example, if AX contains -5 and we do IMULBX, where BX contains 4, the result in AX will be -20. A critical issue with multiplication is overflow, which happens when the result is too large to fit in the destination register. The carry flag, or CF, and the overflow flag, or OF, are set when an overflow occurs. You should always check these flags after multiplication. For example, if we multiply AL containing 255 by 2, the result is 510. This won't fit in the 8-bit AL register, so it's stored in the full AX register, and the carry flag will be set. We can use an instruction like JC, which means jump if carry, to handle the overflow. To summarize, use MUL for unsigned values and IMUL for signed values. Always be aware of the result size and check for overflow. Now let's move on to division and the remainder. Division in assembly is handled by the DIV, instruction for unsigned numbers, and IDIV for signed numbers. The DIV instruction divides a larger dividend by a smaller divisor. The dividend must be placed in a specific register pair before the operation. Let's look at the table. For an 8-bit division, the 16-bit dividend is in AX, and after dividing by an 8-bit operand, the quotient is stored in AL and the remainder in AH. For a 16-bit division, the 32-bit dividend is in the DX:AX pair, and the quotient and remainder are stored in AX and DX respectively. For a 32-bit division, the 64-bit dividend is in EDX:EAX, and the results are in EAX and EDX. For example, to divide 50 by 3, we would put 50 into the AX register, put 3 into BL, and then the instruction DIVBL would result in a quotient of 16 in AL and a remainder of 2 in AH. The IDIV instruction works the same way, but for signed integers. A crucial extra step for IDIV is that the dividend must be sign extended beforehand to ensure the math is correct with negative numbers. There are specific instructions for this. CBW, sign extends a byte in AL to a word in AX. CWD extends a word in AX to a double word in DX:AX. And CDQ extends a double word in EAX to a quad word in EDX:EAX. For example, to divide -30 by 7, we would first move 30 into AX, then use the CWD instruction to sign extend it into the DX:AX pair. Then IDIVBX would give us a quotient of -4 in AX and a remainder of -2 in DX. There are some common pitfalls with division. The most serious is the divide by 0 error, which will cause a CPU exception. You must always ensure your divisor is not 0. Also, make sure the dividend is in the correct larger register pair. And for IDIV, always remember to sign extend the dividend. Next, let's see how to expand simple addition using the carry instruction. When you need to add numbers that are larger than the CPU's native register size, like adding two 32-bit numbers on a 16-bit processor, the standard ADD instruction isn't enough. This is where ADC, which stands for add with carry, comes in. It allows us to chain additions together. The concept is just like manual addition. You add the rightmost or least significant parts first. If there's a carry, you add that carry to the next set of digits to the left. In assembly, we use the ADD instruction for the least significant byte, and then we use the ADC instruction for all the higher bytes. ADC automatically adds the value of the carry flag to the result. Let's look at an example of adding two 16-bit numbers. hex 00FF, and hex 0002. The expected result is hex 0101. In the code, we first load the lower byte of each number into registers and use add FF plus 02 is 101 in hex, which is too big for 1 byte. So the result in the AL register is 01 and the carry flag is set to 1. Next, we load the higher bytes and use ADC. This instruction adds the 2 high bytes, which are both 0, and also adds the value of the carry flag, which is 1. The result is 1. So the final 16-bit result is hex 0101, which is correct. Just as ADC expands addition, SBB, which stands for subtract with borrow, expands subtraction. When you subtract a larger number from a smaller one, a borrow is needed from the next higher order digit. The carry flag acts as this borrow indicator in subtraction. So for multi-byte subtraction, you start by using the SUB instruction on the least significant bytes. Then for all the higher bytes, you use SBB, which subtracts not only the source operand, but also the value of the carry flag. Let's see an example where we subtract 2 from 257 in hex. That's hex 0101 minus hex 0002. The expected result is 255, or hex 00FF. In the code, we first use SOB on the lower bytes. 01 minus 02 requires a borrow, so the result is FF, and the carry flag is set to 1. Then we use SBB on the higher bytes. This will compute 01 minus 00 minus the borrow of 1, which results in 00. The final result is hex 00FF, which is correct. Finally, let's discuss arithmetic operations on decimal variables. Assembly supports B, C, D, or binary coded decimal arithmetic. This is useful in applications like financial software or calculators, where decimal precision is critical. In BCD, each 4-bit nibble represents a single decimal digit from 0 to 9. For example, the hex value, hex 25, in BCD represents the decimal number 25, not the binary value 37. To work with BCD, we use special adjustment instructions after performing addition or subtraction. The key instructions are DAA for decimal adjust after addition, and DAS for decimal adjust after subtraction. Let's focus on DAA. You use it right after an ADD instruction. It checks if the result in the AL register is a valid BCD number, and if not, it adjusts it. For example, let's add the BCD values for 25 and 37, which are hex 25 and hex 37. A normal binary addition gives hex 5C. The C is not a valid decimal digit. After the add instruction, we use DAA. This instruction corrects the hex 5C to hex 62, which is the correct BCD representation for the decimal number 62. Subtraction works similarly with the DAS instruction. Let's subtract 25 from 62. In BCD, that's hex 62 minus hex 25. The binary subtraction results in hex 3D. Again, D is not a valid decimal digit. The DAS instruction placed after the sub adjusts this result to hex 37, which is the correct BCD value for 37. In summary, DAA and DAS make it possible to perform accurate decimal arithmetic in assembly, which is important for specific applications, especially in legacy systems or specialized hardware. This concludes our section on performing arithmetic operations. Thank you.